In hyperscale AI data centers and aerospace systems, hardware failure is not an option. A single downed server or navigation error cascades into catastrophic system losses. When a board fails instantly on the manufacturing floor, it is actually a relief. Hard failures are routine. Engineers isolate the dead component, replace it, and the line keeps moving. This creates a dangerous complacency. Modern surface mount technology lines pump out millions of units, and systems engineers learn to implicitly trust the green pass lights of automated testing stations. But that trust shatters when quality assurance encounters a specific, intermittent nightmare, the marginal fail. A marginal fail is a module that achieves a flawless 100% pass rate across optical, X-ray, and functional testing in the factory. It ships as a perfect unit, only to die intermittently in the field months later. These unpredictable field failures trigger multi-million-dollar product recalls and inflict permanent reputational damage on brands. A factory pass verifies that a board is functional at the moment of testing, but it offers no visibility into the structural integrity of the internal layers. To understand why tests fail, look at automated optical inspection. AOI is restricted to the top layer. They verify external components and smooth solder joints, but see nothing beneath. X-ray attempts to solve this by penetrating fiberglass to view hidden structures, like BGAs. The problem is X-rays analyze density. They struggle to separate structures overlapping tightly along the vertical z-axis. In modern high-density boards with 40 layers, the sheer density of copper vias effectively blinds the X-ray. Microscopic separations vanish into the solid gray background geometry. The printed circuit board acts like an iceberg. The surface looks pristine, but the most complex, defect-prone interconnects are entirely submerged. These undetected subsurface anomalies ship out to the customer. They sit in data centers as latent time bombs, waiting for the right environmental trigger. The trigger for these defects is planted before the board even leaves the factory, during the extreme thermomechanical stress of the SMT reflow process. To melt the solder, reflow ovens force the entire board to endure temperatures up to 260 degrees Celsius, triggering violent physical reactions within the materials. This chart plots temperature against the volumetric expansion rate of the internal materials, highlighting the coefficient of thermal expansion mismatch. Notice the copper line. Its expansion rate remains flat at roughly 17 parts per million per degree Celsius, regardless of intense heat. Now look at the FR4 fiberglass laminate. It starts with a significantly higher baseline expansion rate. The system breaks at a critical thermal threshold called the glass transition temperature, or TG, which hits around 140 degrees Celsius. Once the temperature breaches 140 degrees, the FR4 loses its structural rigidity. Its vertical expansion rate shifts from a steady, linear climb into a violent exponential spike. TG represents the exact thermal boundary where stable material physics transform into a board-destroying mechanical force. We can see this force in action by looking at the microscopic architecture of a single plated through-hole via inside the board. The failure often originates in the drilling phase. Dull drill bits create excessive friction when boring the initial hole. This friction melts the FR4 resin, smearing it across the inner copper layers before the vertical barrel is plated. The result is a compromised bond. When this weakened via hits the 260-degree heat of the reflow oven, physics take over. The FR4 expands aggressively along the vertical z-axis, exerting massive mechanical pull on the rigid copper barrel until the resin-smeared joint violently separates, completely breaking the circuit. Engineers classify this specific structural failure as an interconnect defect. As the board exits the reflow oven and returns to ambient factory temperature, a secondary physical reaction occurs. The FR4 cools and contracts to its normal size, pushing the torn faces of the copper back together, re-establishing a physical connection. Because the torn edges are physically touching, current flows perfectly during the final in-circuit test. The automated system registers a green pass. The defect is now physically fatal, but electrically invisible, waiting for a minor heat spike or vibration in the field to separate the faces again. When these intermittent boards inevitably fail and are returned, suppliers often run standard electrical tests, find the reconnected copper, and issue a "no problem found" report. This causes massive friction between systems integrators and suppliers. forcing a root cause correction requires indisputable physical evidence. The definitive method to counter a no problem found denial is destructive physical analysis, executed strictly under IPC standards. The first and most sensitive step is precision cutting to isolate the exact failing via. Analysts cannot use standard rotary tools. They generate friction heat, which would push the FR4 past its glass transition temperature and create new, false cracks. Instead, they use a specialized diamond saw, heavily flooded with a continuous liquid coolant to maintain absolute ambient temperature during the cut. Forensic engineering relies entirely on preserving the truth. Using the wrong tool accidentally manufactures defects, permanently destroying the actual root cause evidence. Even after a flawless cold cross-section cut, the physical crack is often completely invisible to the analyst. The saw blade's mechanical shearing action drags soft copper across the cut face, physically bridging the microscopic gap. Analysts perform chemical etching with hydrogen peroxide, dissolving this top-smeared layer, exposing the dark, jagged void of the separation. The final verification step is optical microscopy. Standard bright field lighting bounces flatly off the copper surface, washing out the delicate details of the crack. The solution is dark field microscopy. Analysts alter the light source to strike the sample from an extreme oblique angle. This angled light catches the uneven edges of the sub-micron separation, forcing those specific edges to scatter photons directly up into the lens. This glowing fault line is the undeniable physical proof of the interconnect defect, permanently shutting down the no problem found defense. Reliability in mission-critical hardware is built on forensic rigor, using the physics of failure to verify the integrity of the structures hidden beneath the green lights.